In this videotape, we will discuss similar triangles and then the Pythagorean theorem. Two triangles are considered similar if the three angles in one are respectively equal to the three angles in the other. Now, I've taken a very simple example of similar triangles. I have drawn here two equilateral triangles. Here, all the three sides are the same. Here, all three sides, okay, of this triangle are equal. Since we have three equal sides, this triangle is not only equilateral, it is equiangular. Since the angle sum of a triangle is 180 degrees, I know that each of these angles is 60 degrees. Okay, and also here, this equilateral triangle is also equiangular. Therefore, each angle must be 60 degrees. These triangles are similar. Okay? They have basically the same shape. They do not have the same size. If they have the same size and the same shape, then they would be congruent. Okay? If they have just the same shape, okay, as indicated by their angles being equal, then we have similar triangles. It's a very simple case of similar triangles. Let's consider, because they're equilateral triangles, let's consider a slightly more complicated problem over here. Let's start here with triangle ABC. And next to it, I'm drawing a triangle which is similar to it, and I will label it A prime, B prime, C prime, to indicate that there is a relationship between these triangles. Okay? Angle A is equal to angle A prime, angle B is assumed equal to B prime, and angle C equal to C prime. But the lengths of the sides are different. These are similar but not congruent triangles. Now, suppose I were to tell you that the sides of this triangle ABC had length 6, 8, and 12. And I were to tell you that side A prime, B prime here had length 9. And I were to ask you to find the length of this side of the triangle and the length of this side of the triangle. Okay, now there is a key theorem for similar triangles which will enable us to handle this. And the theorem is this. Similar triangles have their corresponding sides in proportion. By corresponding sides, I mean the sides opposite equal angles. Okay, in this triangle, you can tell from the labeling which sides are corresponding. Side AB corresponds to A prime, B prime. They are both opposite angles. Well, this is opposite angle C, this is opposite angle C prime, but C and C prime are equal to each other. Okay, to figure out which side is opposite an angle, if you look at the sides of the triangle which form that angle, they cut off the side here. Okay, the side, angle C is equal to angle C prime, therefore the sides opposite angle C and C prime are in proportion. These are corresponding sides, AB and A prime, B prime. Now, angle B is equal to angle B prime, so AC and A prime, C prime are considered corresponding sides. And the same thing for BC and B prime, C prime. Okay, using this, we can set up proportions to find the unknowns here, namely x and y. Once again, similar triangles have their corresponding sides in proportion. Okay, let's start off by trying to find out the length of B prime, C prime, that is to find x. To find x. If we want to find x, let's start with x. We want to set up a proportion, proportions between the triangles. Now, we can say that x is to 8 as 9 is to 6. Let's follow this through. X, that is B prime, C prime, the side opposite angle A prime here, is to 8, which is BC, as 9, which is A prime, B prime, is to 6AB. We are setting up the proportions. X is to 8. This side here is to this side here. X is to 8 as 9 is to 6. In this particular case, it was very simple to figure out which sides are corresponding because of the labeling of the diagram. Sometimes it's a little harder. The trick is to look for the angles which are equal and to realize that the sides opposite the equal angles are the ones that we consider corresponding. Now we can say x is to 8 is 9 is to 6, and we want to solve for x. Okay, this is a fractional equation. We can find the lowest common denominator, which is 24, multiply both sides of this equation by 24. 8 into 24 goes 3 times, giving us 3x. Here, 6 into 24 goes 4 times. 4 times 9 is 36. 3x is 36. Dividing both sides by 3, x is equal to 12. Okay, we're able to figure out that this side has length 12 units. Okay, now there is another way to set up the proportion. Okay, what we did is to go from this triangle to this triangle, and then from this triangle to this triangle. Instead, we could have said x is to 9 as 8 is to 6. X is to 9 as 8 is to 6, meaning B prime C prime is to B prime A prime as BC is to AB. Okay, so the proportions can be set up in either way. Either you can take one side from this triangle and one side from that and compare it to another side in this triangle, another side in that, or you can stay within, say, the larger triangle, go x is to 9, and then pick off the corresponding sides in the smaller one, 8 is to 6. If you were to multiply both sides here by the lowest common denominator, which is 36, you would also get x equals 12 as an answer. Okay, so we were able to find x. Now let's try to find y. Okay, we know now that x is equal to 12. We don't have to use that directly to find y. We will say that y is to 12. The base here is to the base here. Okay, A prime C prime is to AC as 9 is to 6. Okay, alternately you could have said y is to not, let's see, you could have used the 12 that we just worked out here. We went y is to 12 as 9 is to 6. We could have gone y is to 12 as 12 is to 8, making use of the side that we just calculated. Okay, here, y is to 12. I'm talking A prime C prime is to AC as 9 is to 6. A prime B prime is to AB. Multiplying both sides of this equation by the LCD, which is 12, we get y is equal, here the 12's cancel, you just get y. Here 6 into 12 gives you 2, 2 times 9, 18. Okay, so we have y equals 18 and x equals 12. Okay, now let's consider another example of similar triangles. I'm going to give you a triangle here. And I'm going to finish off a smaller triangle up there in such a way that this line segment is parallel to this one here. This sets up for similar triangles. Let's label this A, B, C, D, and E. It is not difficult to show that triangle ABC is similar to triangle DEC. Triangle ABC, the big triangle, is similar to triangle DEC, the smaller triangle in here. And the trick to doing this is the fact that these two lines are parallel. Okay, these are parallel lines. Think of this side of the triangle as being a transversal. Parallel lines cut by a transversal, the corresponding angles are equal. And that is angle CDE is equal to angle CAB. Parallel lines cut by a transversal, these two angles are equal. On the other side as well, here, parallel lines cut by a transversal, this angle equals that angle. And obviously angle C, which appears in both triangles, is equal to itself. Okay? So angle C is equal to angle C. So we have all three angles in one triangle equal respectively to the three angles in the other triangle. So these triangles are certainly similar. Okay, let me label some sides for you. Let me tell you that DC has length 4. That's from here to here. And AD has length 10. That's from here to here. The base of the large triangle here is 28. This length is 15. And I would like you to find, in the smaller triangle, the length of the base, which is x here, and the length of this side, which we will denote by y. We want to find x and y. By the way, if you'd like to try this problem on your own, you can shut the videotape machine off and turn it back on when you're completed. Okay, let's first try to find x. Okay, now x DE corresponds to AB. They're both opposite angle C. Okay, CD here corresponds to CA. Okay, because these two angles are equal, and CE corresponds to CB. We're trying to find x. Let's say x is to 28. That is, the base of this small triangle is to the base of this large triangle, as this left leg here, the left side of the triangle, 4 is to the left side of the big triangle, which is 14. Don't make the mistake of saying x is to 28. Well, anyway, don't. Remember, we're talking about sides of a triangle. X is to 28 as 4 is to 14. We're using the whole sides of the triangle, not just parts of sides. X is to 28. The small base is to the big base as 4. Okay, the short side here on the left is to 14, the length of the long side on the left. All right, to solve for x, we multiply both sides by the LCD, which is 28. And we get the 28's canceling on the left. We get just x. 14 into 28 gives you 2. 4 times 2 is 8. From this, we found that x is equal to 8. Okay, we can use that, or we can use the other side to set up our next proportion. We want to find y now. Okay, we can say that y is to y plus 15. The short side on the right here is to the long side on the right here. This is y is to y plus 15 as either 8 is to 28 or 4 is to 14. Obviously, it doesn't matter which one we use. Let's use the 4 is to 14. Okay, y, the short side here, is to y plus 15, the long side here, as 4, the short side here, is to 4 plus 10, the long side here. Don't make the mistake of just saying y is to 15, okay, as 4 is to 14. Okay, just don't take part of this. The whole side, we need y for the short side and y plus 15 for the long side. Okay, multiplying both sides of this equation by the LCD, which is 14 times y plus 15. On the left, the y plus 15s cancel, leaving you with 14y. And on the right, the 14s cancel, leaving you at 4 times y plus 5. 4 times, excuse me, y plus 15. Okay? On the left, the y plus 15s cancel. You have 14y. And on the right, the 14s cancel. 4 times y plus 15. Then 14y is 4y plus 60. distributing the 4 through the parentheses, and subtracting 4y from both sides. 10y equals 60. Dividing both sides by 10, y equals 6. Okay, so we were able to find that y equals 6 and x equals 8 in this problem. Okay, now we're going to come back to similar triangles in a moment, but first I want to introduce the Pythagorean theorem. The Pythagorean theorem is a very important theorem in geometry. It has to do with right triangles. If you have a right triangle, let's say the length of the sides here are A, B, and let's C represent the hypotenuse, that is the side that is opposite the right angle. In a right triangle, okay, the sum of the squares, two legs, is equal to the square of the hypotenuse. In a right triangle, the sum of the squares of the two legs, remember these two sides, in a right triangle, the two sides, okay, this is the hypotenuse and the other two sides are called legs. The sum of the squares of the two legs is equal to the square of the hypotenuse. A squared plus b squared equals c squared. By the way, the converse of the Pythagorean theorem is also true. That is, if you have a triangle, it has three sides, so that the sum of the squares of two of the sides is equal to the square of the third side, then that triangle must be a right triangle. So it can be used if you have a right triangle to say find some of the sides, or if you have the sides to prove that a triangle is in fact a right triangle. Okay, let's work out some examples using the Pythagorean theorem. Okay, in these examples I want you to find x in each of the following. Okay, first example, here's a triangle, 6, 8, it's a right triangle, and I want you to find the length of the hypotenuse, okay, which is denoted by x. Okay, since it is a right triangle, the sum of the squares of the leg is equal to the legs equals the square of the hypotenuse. That is 6 squared plus 8 squared equals x squared. A squared plus b squared equals c squared. Using it here, 6 squared plus 8 squared equals x squared. 36 plus 64 equals x squared. 100 equals x squared. Now, we have here a quadratic equation. There are actually two roots. Taking square roots, we get x equals 10, x equals minus 10. But since this is a practical problem here, and x represents the length of this side, we're not interested in x equals minus 10. Okay? Because you can't have a side whose length is negative. So in this case, we will only take the root x equals 10 as the answer. 6, 8, the hypotenuse must be 10. Let's try another example. Here's a right triangle. Let's say I give you the length of this leg, 24, and I give you the length of the hypotenuse, 25, and now I want you to find the length of the other leg. See, here we wanted to find the length of the hypotenuse. We knew the two legs. We wanted to find the hypotenuse. We said the sum of the squares of the two legs equal to the square of the hypotenuse. Now, however, we know the hypotenuse and one of the legs, we want the other leg. The sum of the squares of the two legs is equal to the square of the hypotenuse, so x squared plus 24 squared must be equal to 25 squared. X squared plus 24 squared equals 25 squared. The square of the hypotenuse is standing alone. Okay, now, x squared plus 24 squared, which is 576, equals 25 squared, which is 625. Subtracting 576 from both sides, x squared comes out equal to 49. Just do the subtraction. X, therefore, is plus or minus 7, but in this problem, okay, because it's the length of a side, we'll just take x equals 7. Okay, so here, x equals 7. That's our answer. Let's try another example here. The length of this leg we'll call x, the length of this leg x plus 7, and the length of the hypotenuse 13. Okay, we're interested in finding x. Okay, as before, the sum of the squares of the two legs is equal to the square of the hypotenuse, and be careful to use parentheses here when you have the x plus 7. It's more than one term that you're squaring. Okay, now x squared plus, now x plus 7 squared, it's x plus 7 times x plus 7. You just don't square the first and the last. It's the first squared, then the outer and the inner. If you were to write x plus 7 times x plus 7, each come out to be 7x, so it comes out 7x and 7x, 14x, plus 7 squared, which is 49, equals 13 squared, which is 169. Okay, remember, x plus 7 squared should be thought of as x plus 7 times x plus 7. So using FOIL, you get x squared plus 7x plus 7x plus 14x plus 49. Okay, now on the left we have 2x squared plus 14x plus 49 equals 169. And unlike, well, this is also a quadratic equation, but this one, since we have a linear term, first degree term as well, we're going to try to solve this one by factoring. Okay, not by the method of extracting roots. Okay, what distinguishes this quadratic equation from the others is that we do have an x term here. Here there was no x term, no first degree term, neither was there one over there. Okay, they all give rise to these quadratic equations, but now we have an x term as well, so we're going to try to solve this quadratic equation. We know that if factoring works, it's usually the easiest method, so we'll give it a shot. 2x squared plus 14x, subtracting 169 from both sides, 49 take away 169 gives you minus 120. Okay, equals 0. And we notice that 2 is a factor that all these terms have in common. We can factor out of 2 and be left with x squared plus 7x minus 60. 2 times that is equal to 0. And we'll now try to factor this quadratic equation, this trinomial here. And we're looking for two numbers multiplying to minus 60, adding to plus 7. And the answers are plus 12 and minus 5. Checking this by FOIL, x squared minus 5x plus 12x gives you the plus 7x and then the minus 6. Okay, if the product of two numbers equals 0, that means either this number equals 0 or that number equals 0. This gives rise to x equals minus 12, which we will reject in the same way we rejected all the other negative solutions that we got to the problem. And here, adding 5 to both sides, x equals 5, which is the answer. Okay. If x equals 5, then this triangle here has this leg equal to 5, this equal to 12, and the hypotenuse 13. Okay, now certain triples of numbers work in the Pythagorean theorem. These triples of numbers are called Pythagorean triples, and it would help you in your work if you knew a few of them. Okay, let me make a list for you. A squared plus b squared equals c squared is a Pythagorean theorem. I will list A, B, C triples that work in this theorem. Okay, the most popular, 3, 4, 5. Okay, 3, 4, 5. If you knew, for example, that you had a right triangle and two of the sides were 3 and 4, then the third side would have to be 5. Okay, 3 squared, that's 9, plus 4 squared, 16. 9 plus 16 is equal to 5 squared, 25. Another Pythagorean triple is the one that we just discovered over here. We worked out this one. 5, 12, 13 works. Okay. 5 squared, that's 25, plus 12 squared, 144. Gives you 169, which is 13 squared. Okay, the one that we worked out in this example as well, okay, is another common one. 7, 24, 25. And one last one, 8, 15, and 17. Okay. It might be to your advantage to memorize these. If you see, for example, that you have a right triangle, if you know the hypotenuse is 13, one of the legs is 12, without any further calculation, you would know that the other side had to be 5. By the way, not only are these Pythagorean triples, but any multiple of Pythagorean triple is also Pythagorean triple. So, for example, if you multiply the 3, 4, 5 by 2, you get 6, 8, and 10, okay, which came up in an earlier, I think it came up in the first example that we worked out today. Okay, these triples and any multiple of these triples, okay, work in the Pythagorean theorem. Let's try another example, mixing what we now know about the Pythagorean theorem with area and perimeter of triangles. Let's say we have a right triangle, and I tell you that this leg has length 9. The hypotenuse has length 15, and I ask you for the area and the perimeter of this triangle. Find the area and the perimeter of this triangle. Okay, I think all of you agree that the big thing is to find the length of this leg here. If I could find the length of this leg, I would then be very easy to find the perimeter of the triangle, the distance around the triangle. You just would add up the lengths of the 3 sides, 9 plus x plus 15. And similarly, you would also be able to find the area very simply. The area of a triangle, 1/2 base times height, or 1/2 x times 9. X being the base, 9 the height, because it's a right triangle. You can use the leg as the base and the height. Okay, so let's try to find x. Using the Pythagorean theorem, 9 squared plus x squared is 15 squared. 81 plus x squared is 225. X squared is 225 minus 81, which comes out to 144. X is plus or minus 12. I'm only interested in the plus 12 answer. X is equal to 12. As I mentioned earlier, if you were familiar with the Pythagorean triples, you have 3, 4, 5. Okay? Therefore, any multiple of this is also a Pythagorean triple. 3 times 3, 4 times 3, 5 times 3. So if you could say, well, 9 and 15 here. You were given the 9 and the 15, and you say, this is 3 times 3, this is 5 times 3, and it's a right triangle, and this must be 4 times 3. In other words, a 3, 4, 5 right triangle is 5 multiplied by 3. Okay, so some of you might find that useful. 3, 4, 5 multiplied by 3 gives you 9, 12, 15, okay, as a right triangle. Okay, now just finishing up the problem. Since I already know x, I can now find the perimeter and the area very simply. The perimeter, P, is going to be 9 plus 12 plus 15. Just adding up the lengths of the 3 sides of the triangle, and you get 36 units for the perimeter. 9 and 12, 21 and 15, 36. The area, 1/2 base times height, or 1/2 the product of the legs, 1/2 12 times 9. Okay, 2 into 12, 6, 6 times 9, 54 square units. for the area. I would like to finish up this videotape with another example which combines both the similar triangles that we studied earlier and the Pythagorean theorem that we've just learned, and also a little area and perimeter as well. Okay, I'm going to construct a triangle in the following fashion. I'm going to start with a right triangle, like so. I'm going to tell you that this leg has length 6, and the hypotenuse has length 10. Then I'm going to extend this leg here an additional 12 units. All right, and also extend the hypotenuse here. And from this point, 12 units, I'm going to form a right angle and continue down until I hit the extension of the hypotenuse, forming another right triangle. We have two right triangles. Okay, the side here, 6 is specified, the hypotenuse, and that leg there of 12. Okay, and what I want you to, okay, also I'm going to give you one angle in the triangle. In all of these I'm going to give you here, this angle is 53 degrees. And let me label these A, B, C, D, and E. Here's what I want you to do. I want you to show triangle EAB is similar, that's triangle EAB is similar to triangle BCD. I want you to then, let me label some sides. Let's call this X and this Y. I want you to find X. I want you to find Y. And then I want to find the area of triangle BCD. I could also ask you for the perimeter. Okay, once you find the area, you're just going, once you know the three sides, you're just going to add up the lengths of the three sides to find the perimeter. Okay, that's our object. By the way, I could have just asked you the last question here, find the area of triangle BCD, and had you go through the same amount of work. Whereas to find, well, you wouldn't need the, I guess, the hypotenuse here. You wouldn't need Y and the 12 to get the area of triangle BCD. So if we add in, find the perimeter of triangle BCD, you would have to find X and Y, even if you weren't asked to find them to begin with. Okay, now the first thing I want to do is to show that these triangles are similar, which means I have to show that 3 angles in one are respectively equal to 3 angles in the other. Working in triangle BCD here, I know that this is a right angle with 90 degrees, and this is 53 degrees, giving me a total of 143 degrees. But I know the angle sum of a triangle is 180 degrees. That leaves 37 degrees for this angle in here. It's 37 because 37 and 53 gives me the 90 and 90 for 180 in this triangle. If this is 37, I know that this is 37 as well, since we have here straight lines intersecting, the vertical angles are going to be equal. If this is 37, this is 90, that means this must be 53, since the angles in this smaller triangle here also have to add up to 180 degrees. Okay, so it's easy to show that these two triangles are similar because the angles in EAB are 37 degrees, 53 degrees, and 90 degrees, and so are the angles in triangle BCD, 37 degrees, 53 degrees, and 90 degrees. So the first part is completed. Now we want to find X and Y. Although you weren't asked to find the length of AB, you're going to have to find that first. You see, what we want to do is set up, since we have similar triangles, we want to set up proportions with corresponding sides. Okay, unfortunately, we don't know enough to set up our first proportion, so we want to find X. You could say X is to 12. Okay, the hypotenuse of this triangle is to 12, the side opposite the 53 degrees, as the hypotenuse here, 10, is to the side opposite the 52 degrees, but we don't know that. So first we're going to have to find the length of AB. Let's call that Z. Okay, so even though you weren't asked for it, you have to find z first. Now to find z, we're going to use the Pythagorean theorem. Okay, 6 squared plus z squared is equal to 10 squared. 36 plus z squared is 100. Subtracting 36 from both sides, z squared is 64. Z is plus or minus 8, but we're only interested in the plus 8. Z is equal to 8. Okay? You could have also done this by saying, this is 3 times 2, this is 5 times 2, therefore this must be 4 times 2. It's a 3, 4, 5 triangle double.